So when we calculate boiling point elevation or freezing point depression, it's a very simple equation. Um, they're both very similar in the equation, and I've annotated a whole bunch of things here. So first, let's note this is delta T, so that's the change in the boiling point of the solvent, okay? And so we have to remember that delta T is going to be here T final minus T initial. And I'm going to do a sample calculation so that we can get, we can use this formula to get the change in boiling point, but we also want to be able to use this to actually calculate the new boiling point, not just the change in boiling point. So there's that Van 't Hoff factor. This capital KB is, look, the mole boiling point elevation constant for the solvent. You will be given that constant. And then this lowercase m, that's the molality. So I told you this would come back, the molality. So if we look at the freezing point depression equation, it's very similar. The only difference is instead of using KB, you use a different constant, Kf, which is the molal freezing point elevation constant. Oops, that should say molal freezing point depression constant. Okay, let's do a sample calculation. So here's a whole bunch of stuff, big problem to calculate. And if you already have noticed the exam 4 module, this is going to be very similar to your free response problem for exam 4. You're welcome. So let's do it. So part A, calculate the vapor pressure of water at the approximate temperature of this room. I'm not going to do this calculation, so this is given in your chapter 10 notes. Let me just tell you really quick which example that is. So I did that example already. And let's see here. I believe that's example, I think it's 10.1 or 10.2. Okay? So check out that in the notes. Whenever you're told in the approximate temperature of this room, you could use 298 K. You could use room temperature. Okay? And so I'm not going to do this part. I'm going to say we've done this already. And I'm going to look at that value I got in the problem that I did from the lecture. Let's see here. I just turned it away. 27.9 torr. So I'm going to use that as the vapor pressure. But you should absolutely be able to use the Clausius-Clapeyron equation to make this calculation. Okay? So I'm going to say number 1A, use Clausius-Clapeyron equation. 27.9 torr should be your answer for 298K. Okay. B, so this is going to be the new stuff. A solution is made by dissolving 1/4 standard US cup of table salt, and there I gave you the density of sodium chloride, in 2 standard US cups of water. Calculate the vapor pressure of this new solution using your previously calculated vapor pressure of the water above. Okay? So I'm not going to do that one either because I just did a problem very similar to that in your previous notes. So number 1B, so I want you to follow along with example 11.1. Make your best effort to calculate this. Okay? And I'm going to put the calculations in, well, let me see here. I'm looking at the time. Actually, you know what? We've got plenty of time. Never mind. I'm fickle today. So we've got plenty of time. So let's go ahead and do it. Okay? So the first thing that I need to do to calculate the vapor pressure reduction, right? I recognize P solution. It's going to be chi solvent times P solvent. So we know 27.9 is the P solvent. So really what I have to calculate here is chi solvent, which is going to be the number of moles of H2O divided by the number of moles of H2O plus the number of moles of NaCl. So first, to calculate the number of moles of H2O, it's 2 standard US cups of water. This is so dumb to me. 236.5882365 milliliters Why can't we just use 250 milliliters like they do in Europe? Anyways, so that's going to be 2 times 236, I'm just going to say 0.59 milliliters. And I want to convert this to moles. So I recognize in 1 milliliter of water, there's 1.00 grams, and there's 18.01 grams in 1 mole, okay? So that's going to be 2 times 236.59 equals, and then let's see, so times 1 gives me the same number, and then divided by 1 divided by 18.01 equals, and I get 26 let's say 27 moles of water. So now my number of, not ethanol, but sodium chloride, okay? My number of moles of NaCl is now going to be, so it was 1/4 cup of table salt. So that's 0.25 times 236.59 milliliters. The density of sodium chloride is 1 milliliter in 2.16 grams. And sodium chloride is, off the top of my head, chlorine is 35.45 plus sodium is 23.01. So 58.46 grams of sodium chloride in 1 mole. Okay, so now let's see here. So that's going to be 0.25 times 236.59 equals times 2.16 equals divided by 58.46, and that gives me 2.19 moles of NaCl. So very quickly here, Chi solvent, so the mole fraction of H2O is 26.27 mole plus 26.27 plus 2.19. So let's see, so that's, I'm going to leave that in the calculator, plus 26.27 equals 1 over x trick times 26.27 equals, that sounds about right, 0.923 is the mole fraction. So B is just 0.923 times 27.9. So let's see, that times 27.9 equals, and a pretty significant amount of vapor pressure lowering, 25, let's say 0.8 torr for answer 1B.